Okay, so today we're going to see some loose ends since pretty much the beginning of this class, and we want to tie these ends, and I want to start by. Okay, let's see. Remember, there were some constructions that we had seen on categories, specifically these two. If you have a poset, I can see the poset as a category, and the idea is that pretty much you look at the Hasse diagram where the arrows means that something compares to something. And also, remember this construction where you start from a monoid. You start with a monoid, and the idea is that you see this as the category that has a single object that has nothing to do with the monoid. It can be anything you like, and then for each member of the monoid, you see it as an arrow, as an endo arrow from this object to this object. So these are the members of your monoid, while here, the members of your poset become actual objects in this category, and you denote the fact that something compares with something by drawing an arrow. So these two things are quite crucial as examples of categories and as constructions, because they show us that we can see a category as a generalization of a monoid and as a generalization of a proset as well. I say proset because we want to permit maybe things like that without necessarily being an isomorphism or the same object. Okay, so with this in mind, now that I've reminded you how these constructions work, and remembering what a functor means, let's try to find out what a functor from a category like this to a category like that does. So the idea is that I have two posets or prosets, what you like, and I look both of them as if they were categories. So now I'm looking at two categories, and I'm asking the question, what is a functor from one to the other? I hope at least the question makes sense, and let's try to figure out what this means. So what does so you have a poset here, and you have your other poset there. So this is C of P and this is C of Q. And the question is what can I say if I know that I have a functor from one to the other? And here you have arrows, of course, and we know that functors can act on objects and map them to objects, and on arrows and map them to arrows. Arati, yes? Okay, so exactly this thing is nothing more than a monotone function. It's what, but let's not confuse this. The question was not like what are the arrows in the category of posets. So this is the category of posets. Just to emphasize this, I'll make it like that. This is the category called poset or proset. So somewhere here is an object that codifies P, or that is P, if you like, and here is Q. So the question I was asking, and I hope Arati knows that, was not what is an arrow from P to Q. We have defined this to be a monotone function from P to Q, or a function that respects the order. The question was, forget this category, look at this category and this category, and what would be a functor from one to the other. Right? Okay. So the idea is then that you will map an arrow like this. Let's call this A, B, and I would like to say F, but I'm in a proset, so it doesn't make sense to worry about what is the name of an arrow, because in a proset either there is an arrow or there is not an arrow. So especially in this case, I could just decorate every arrow with a less than or equal to, which means that the information that I have from this arrow is that A is less than or B. So the idea is, where will I map A? Okay, first of all, I have to map A somewhere and B somewhere. So let's say here is f of A, and let's say here is f of B, and I have to do something with the arrow. Well, I need to map it by the functor laws. I could not map it to some other object. It has to respect source and targets, which means that I have to map it in one of these arrows that go from F to A to F to B. Which arrow will I pick? Yes, Manolis?
I mean, either there exists just one or none, which would...
I will never have the problem of picking the correct arrow, because if there is an arrow, it's unique. I will only have a problem to pick an arrow if there are no arrows. So this amounts to what? I'm looking essentially at a function from the underlying set of this poset to the underlying set of this poset, in other words, a function, such that if you have an arrow from A to B, then you want to have an arrow from F to B. And if I translate this back to the language I knew when I was studying posets, this is just, okay, this is a famous and kind of funny or pejorative or whatever you want to call it, categories just, where some categories tells you that, this thing, profound thing that you, or this thing that you really like is just, and then followed by something. So someone could say that monotone functions are just functors from a prosetal category from a category that came from a proset to another category like that. Probably this is not the definition you want to give someone trying order theory, but it's kind of soothing or nice to see that something and a lot of different things can be described and put in a framework, in the same framework with just different clauses. So a bit faster now, what would the situation be if I look at monoids? So now I have two monoids, M and N, and the idea is that I see both of them as the corresponding categories. Again, do not confuse this with the situation down here, which is the category of monoids in which I have an object for M, for the monoid M, and I have an object for the monoid N, and I have possibly many arrows here denoting the fact that each of them is a homomorphism from the monoid M to the monoid N, and so on and so forth. Okay, so this is, forget the category of monoids, and look at the monoid M as a category and the monoid N as a category, and I ask the same question, what is a functor from this to that? Ideas? Okay, let's see what a functor should do. It should map objects to objects. How does N look? It has a single object, let's call it the North Star, and it has its arrows. Essentially, the arrows here correspond to the elements of N, and the arrows here correspond to the elements of M. Okay, so what should the functor do? It should map all objects to some object there. There is only one object here, so I know that my functor will just map this to that. So telling me this, I have no extra information. But it must also map arrows, and now there is plenty of choices possible for each of these arrows, and I have to see what the laws of the functor laws make me do, right? So there are two functor laws. One tells me that I have to map the identity, let's make it blue, to the identity, right? So I would write this like that. Okay. Of the identity of the bullet, this has to be, it has to be technically, if I want to be like faithful to what the law says, this functor law to the F of the bullet, right? So the get identities commute with functors, let's say like that, but I know what this thing is. What is this thing? Yes? Star, yes, okay. So I know that the identity here will be mapped to the identity there, and maybe I'm starting to guess what the other law will also translate to. So the other law is that functors respect compositions, which means that I need more space. Okay, so which means that if you take an arrow, let's call it A, composed with an arrow let's call it B, you have to map it to whatever arrow on the other hand side you mapped A, composed with whatever arrow you send your B to. But now, remember what composition means here, because in order to define this category, I need to define what composition means. And we said, for compositions, consult the monoid. And we said for picking which is the identity, consult the monoid. So pretty much this is all the information that the monoid gives, tells me how these things behave. So this would be something like f of a, the operation in M, B, right? And this should be f of a, but now I'm composing the arrows of the other category, and the functor, the definition of this category tells me that this comes from this. Conclusion, I'm trying to get you to familiarize you with this whole idea of just. Yes, Manolis?
It's just a homomorphism from one monoid to another.
Yes, so a functor between these specific categories is just and, or actually it's the other way around. Yeah, so if you want to, if somebody tries to tell you, I have a good definition, I know what a homomorphism of between monoids is, you look at it and then you say, this is just a functor from the category M to the category N, okay? Questions? No, okay. The next notion I would like to define is one that comes quite a lot, shows up quite a lot, is that of a groupoid. And we will play the categories game, and we'll say, a category is just that thing in a couple of minutes. So by the name, I'm expecting this to be some kind of generalization of a group, and it indeed will end up be, but this is just a name that we give to categories where we have that all arrows are inventable. A category where all arrows are iso. Remember, iso just means invertible in our vocabulary. Okay, now the question is, why would we call it like that, and how can we justify that this is a generalization of a group? And in order to do that, I just have to tell you that the group is just, right? Is just groupoid. Now, if I stop here, it's not a generalization, it's the same thing. But it's a special kind of groupoid. It's a groupoid where... Has anybody spotted this? It's once you get used to it, it's quite obvious, but I mean, it's probably not so obvious if it's the first time you see it. Areti? Where all the functors are what? No, I think I know why you are saying this. It doesn't really make sense to talk about functors inside the groupoid, because look, a groupoid is a category, right? So inside the category, I don't have functors, right? Functors are what will get me from a category to a different category. So the definition of a groupoid limits me to a category that looks like that. For each arrow that I have, I know that it has an inverse, right? And I don't know, maybe it looks like that. All of these arrows that I'm drawing, I know that are invertible. So this is what a groupoid is. Obviously, it's like adding another axiom to what, another law to what the category should satisfy. So I hope we agree that groupoids, the way I have defined them, is just a special category, right? A kind of category where every arrow is iso. Normally, you don't see that in categories, but if in a category all arrows are isos, you have a groupoid. So yes, what were you? The compositions, what do you mean by composition? Inside this category? Not necessarily, because look, if I compose this with that, both of them are isos, right? But they are not, I don't get the identity. Of course, if I compose this with its inverse, I will get the identity, but this is what iso means in this case. Yes?
Is it just a groupoid where the objects are the arrows?
I could stop you the moment you said the S sound. Not objects. Okay, so it's a groupoid with only one object.
What?
Okay, let's see this. With only one object. So if I forget about the rest, right, and I have only one object, the fact that I'm in a groupoid means that all my arrows are invertible. But let's look at the laws I already had ever since I knew that it was in a category. I had identities, associativity, right, and identities. And what was missing to see this as a group was inverses. But now I know that all arrows are invertible. So if I look, okay, this is always a bit dishonest. I'm not saying that this is, like the group is the groupoid with only one object. Where is the group hiding here? If I look at these arrows, right? Yeah, sorry, yes.
The elements of the group are the arrows.
The elements of the group exactly would be the arrows, the endo arrows of this object, and I have nothing else to say. Sometimes you will see a definition of a groupoid that relaxes the definition of a group in a different way, and this way is saying that the operation is not necessarily total. It's a partial operation. It's not a different definition, pretty much it amounts to the same thing, the idea being that in order to compose this with that, I need to check. There may be some arrows that are not composable, like if you take this arrow and compose it, try to compose it with this arrow, they should be not composable, so you don't have so your multiplication ends up not being totally defined. But from the point of view that we are seeing things, the definition that would make more sense would be this just thing. And before we get to the punchline of this kind of joke part, I hope you can see the kind of humor that's there, but actually you can appreciate the idea of putting everything in the same framework. Okay, so if we let's look at this oid here. There is even a concept called oidification. You get something and you do to it what you did on group to get a groupoid. Okay, so if you do this, if you start with a group because you know groups, and you say, aha, I will generalize it. What was a group? It was a category with only one object where everything was an iso. And what kind of generalization happens when I pass from a group to a groupoid? I forget the restriction that there should be only one object. I still keep the idea that everything should be invertible, but I forget this restriction and I reach a groupoid. So question is, what happens if I do the same to a monoid? Again, when I'm saying group here, I mean it's a group. I see it as a category that has some extra restrictions. It has only one object, and all arrows are isos. So when I look at this monoid, the way I wrote it, it's again, I look at it as a category which has one restriction, right? It only has one object. So it's a category with only one object is called a monoid. If I give you a category, I tell you it only has an object, look at these things, there is a monoid, right? So question, what goes the other way? What goes on what's here, right? Solve this. I mean, you can guess the word. It's the oidification of a monoid, so I'll write it down. It's a monoidoid. It sounds bad, I know, but okay, that's why it's kind of funny. But what is it? So I get a monoid, which is something that looks like that, and I say, the restriction is what? I mean, I don't stick too much to the picture, because if you stick too much on the picture, you might think that I will permit more things like that, but actually the restriction that I have is simply, okay, first of all, that's wrong. My design is wrong here, because I have drawn everything to be invertible, and this is not the case for a monoid. Okay, so it looks, let's make it better. It looks like that. Okay. But the only restriction that I have is a category with only one object. No restriction about the arrows, being iso or whether they exist or they don't exist, only one object. So I drop this restriction. But if I drop this restriction, what do I have?
Just a category.
It's a category. I mean, the only extra thing I had here was, aha, it should have only one object. Okay, forget that. You're a category. So to throw it backwards on the categories, you say, okay, you like categories. A category is just a monoidoid. Okay, so in this sense. Okay, so I hope this thing makes some sense. Now you will get some jokes you would not get earlier. And if there are no questions, okay, perfect. So again now, let's dive in some category that I know nothing about. And I will want to define like some concepts, categorical concepts. We have seen a lot of them, like what is a product, what is a terminal object, what is a mono arrow, epic stuff. We've seen some epic stuff, okay? So what I want to define now is what it means to be a group object. It's called like that, group object, in a category. And again, just like with all these categorical definitions, I'm not saying that every category has something that behaves like that. I'm just giving a name to this behavior. And now if I'm in any category, I can ask, in this category, does such and such exist? And if it exists, by any chance, is it interesting? By any chance, do I already know this and I'm discovering that it's from a different angle? Yes, okay, so there are some questions, yes. So there is.
I can see the intuition of a groupoid.
Okay, you're back here.
Yes,
okay.
having only one element, if I think of a finite group generated by only one element, but what if the group is generated by two elements?
Okay, save your question for like in a few minutes, that way, because I know, I used to believe during the previous class, you weren't here, but I used to think that everybody knows what freely generated means. I found out in the last 3 minutes that I could not count on this, so one of the subjects that we will see here is this. So just in order for your question to be understandable by everyone, ask it again in like, I don't know, 30 minutes or something. As soon as I come back to say this. It will not be a problem, okay, so, but let's discuss it once we know what freely generated means. And actually one of the things that I need to do today is define this in a categorical way. Because I think that like Sotiris has seen what a freely generated group is, maybe hasn't seen what a freely generated monoid or a freely generated lattice or a freely generated whatever it is, or maybe he has, I don't know. But the idea is to put all these things in the same framework so that the definition ends up not requiring anything special that a group has to offer, but put it in a categorical setting so that we understand better what's going on. So we will get there, I hope, and then you will see that this will not be an issue. And what was the other question? Here, there is no question here yet. Have I asked? Maybe I asked something. Yes, what was it?
Ένα group object σε ένα category δεν θα είναι οποιοδήποτε object με πολλά endoarrows.
You mean ISO arrows, ISO endo arrows? No, I mean, if you look at any category and you pick a single object and you look at all the automorphisms of this forms a group. The automorphs form a group. It's not what we end up calling a group object. Like a group object will again, it's kind of misleading in the same way that the product was misleading. Remember, in order to define the product of A and B, I had to fix A and B, and then what was the product? It was not just an object, right? I emphasize this a lot. I hope we are fine with this. It was configuration of this form. So it was all this triple that ended up being a candidate for a product. And all these categorical definitions we have seen so far have the same spirit. Among all the things that do this, the best one will be the product. And the best one usually means the initial or terminal thing, depending on which one makes sense to call it the best. Usually one of the two is completely useless. So you don't really have you would never like define the product as an initial thing. Okay, so I will not repeat the definition of the product, but I just want to remind you that it was not just an object. Even though we say that this thing is the product of A and B, and after we have proved a very strong kind of uniqueness, which was the unique up to unique isomorphisms, we said, okay, I will denote it by that, even though that I know that it's not really unique. And we have seen also that it makes a lot of sense to change and pick your favorite names for these projections depending on what you want to decode. Remember that from each group I can project out to get the carrier set and the operation and the identity, the inverse, and the laws also, if I put it in a type theory context. And I would definitely not want to have to remember all these things and project out with like the first projection and the second projection or whatnot. I would like to see something like meaningful names, right? So this would be like the op, and maybe somewhere down here I have something called laws, and maybe this one has like three things, like the associativity and the, I don't know what, the identity laws, or the unit, maybe it's a better name, unit, and the inverses, etc. Okay, so names matter, and even though we have this uniqueness, it makes sense to pick your favorite names. So coming back to what a group object is, it will again not be just a single object, it will be a whole diagram, a whole configuration. Object with certain arrows and stuff like that. And I'll start drawing it and you'll get the idea. Mysteriously I will call it G. So if I have an object in my category, let's call it G, and also in it I have these things, an arrow like that, which mysteriously I will call M, an arrow like that, which I will call I, and an arrow like that, which I will call U. Okay, let's pause and see if we understand everything I have written here. So remember, 1 stands for a terminal object, and we have seen this idea that if I have arrows from the terminal object into something, it's like picking, fixing a static element there. So what the set theorists would do like that, the set theorists would say, aha, I. We have seen this correspondence in the past, so I will not spend time on it now. But okay, let's look at that and let's see what these things are supposed to encode. I mean, I hope someone will guess it. We will make my experience easier here. Somebody help me. Konstantinos. To U, no, wait, it could not be the inverse, because the inverse is a unary operation. Maybe that's why you thought of the U. It's a unary operation, but unary operation means it takes something of G and gives you back something of G. While this one takes what? Remember, this is just a unit. It has just the empty tuple in it. It just has nothing on it. It's just a single thing on it. So it cannot really get something from G. Every time you call it, it just picks a single specific element inside your group. So you, Arati, U comes from? What you're saying is that I start with a pair of things from the group and I maybe do this or that. I don't have this yet. We will have this very soon. I don't have this yet because when I start to say, aha, I'm here and I can do either that or that, it's the beginning of a diagram that I would like to commute. And there are no cells here. I mean, if it was something like that, another path here, you would say, aha, you start from here and you can either do this or you can do all those things. And it amounts to being the same, so this would be the commutativity of this. But in this sense, I don't have any meaningful two different paths that get me from somewhere to the same target. So this question does not enter already. Manolis, what was your pick? Lazaros, sorry. Yes?
U is like the ability to pick the unit.
Okay, so U is, if I think of the groups that I know, okay, so what would you say, what is the usual definition of a group that you see in the first or second semester where you see it? It's like, it's a set, okay, so let's pretend for the time being that that this category is set. The whole point is to liberate me from this idea, okay? But let's see what happens in set. So these are sets, so it's a set together with what things? a binary operation, it's a binary, a unary operation, this will be the inverses, and a zero-ary operation, which you will not see it as a zero-ary operation when you're first studying groups, but you say a specific element of the set, how you say, a pointed element or a, I don't know. Does anyone have a good word for that? Anyway, which you call a unit, okay? Such that blah blah blah, okay? But we have everything up to the such that part. Do we agree? I have a set, a binary operation, a unary operation, and a zero-ary operation, and hopefully the names help you think. Maybe it didn't happen that well, so this would be like the multiplication, the inverses, and the unit. But the fact that I give you this name is just to be indicative. It doesn't mean anything until I say such that, okay? Now, if I say such that and I start listing equations, the problem will be like if I say the M of A, B, so this should be what? Multiplying the product of A, B with C should be the same as multiplying A with the product of B, C. Okay, if I start doing that, I'm not in the right track because I'm back to thinking in points, right? What is this A and B? Say, there are elements there. So I want to try to describe all the group laws without only by arrows and commutative diagrams. So let's try to do some, at least one together. Let's try to do the inverse. This is usually the easiest one. I mean, first of all, it's a unary, and so you don't have to worry too much about things. And the first time you see things like that, you might be kind of confused, but let's see if we have all the tools we need in order to express this idea. So let's start with this one. I want to express the idea that this arrow picks an inverse, right? So the thing that it picks deserves the name inverse. But I cannot say, give me an element, because I lost the generality I'm after here, right? And all these things will end up being in the way, kind of the way that Areti was describing a couple of minutes ago. You start somewhere, you do this, and a different person does that, and you end up in the same thing, okay? So what are the two different things that happen for, we can do this or even that, but okay, let's start with this. Ideas. I will give you a hint. Essentially, I want to describe that the I of an x multiplied with an x is equal to E, right? Okay. I have a way to describe this E, because this guy picks E inside the group. I have a way to describe this function. It's this one, okay? So in my diagram, there will be some kind of, this thing should definitely appear at some point, because eventually I will have to multiply two members of the group. And how do I multiply them? With arrows with this arrow coming out of G cross G. So my diagram will involve, will not be something like, that looks only like this. The law I'm trying to, and of course, if I look at the equation, this is kind of expected, because what was the equation? That x times inverse of x is equal to u. I mean, if you look at this equation, it involves all these three things, right? So, okay. So let's see. Yes.
Probably wrong, but close.
Give it a shot. Yeah.
It looks like mi comma I, like something like mi comma I equals u, but still I'm doing a type error there.
Wait. It's a type error in the sense that what I'm after is like a diagram. So the answers I'm looking for are like, first of all, describe how the diagram looks like. I mean, it has a G here, a G cross G there, another G cross G, another G, and one. So, and then we put the arrows, and then the idea is saying the following. This thing commutes will amount to the law that this is an inverse. And a different diagram will amount to the law that this is associative, and a different diagram will amount to this thing picks really the an identity
It
element.
looks like if I take I in a row that I should end up with you. But,
You mean I and I again?
yes.
So you mean that if you get this, okay, you can describe this. You get the inverse, and then you get the inverse again. So what you're saying, let's start with.
And then I multiply the two results. Yeah.
So you would like to do something like that. Okay, let's start with this. It's not the answer we want. This describes a law, but which is actually a valid theorem of group theory, but it's not one of the laws. What is the theorem that Sotiris is describing? That the inverse, it's this equation. This is what you're describing, but there is something problematic here that I need to fix. It's easy to fix. What's the little problem here? Yes?
It's not you, it's the identity function.
It's not, oh, yes, okay. Yes, okay. Exactly. Okay. So, sorry. The fix I was thinking was a different one. It was a wrong one. This is the correct fix. It has nothing to do with you, it's the identity. The identity arrow, which is also called like that, confusingly. Okay. We are on the right track. We described something which is valid in every group, but it's not one of the laws we want to describe. You're describing that inversion is involution. No, sorry. Idempotent, right? That's a word, right?
Yes.
Yes, okay. So this inversion is idempotent, I think. Okay. No, it's an involution. And idempotent would be a binary one such that xx is equal to x. I'm almost sure, but I may be confusing the terms. Okay, it doesn't matter, or it does, but not right now. So we want an answer similar to what Sotiris gave. Manolis.
So we want to go from g to g through the inverse function, and then we want to go to g squared with the composition of the identity and the inverse. It's kind of
Give me a second. So first of all, you will want to do this from the inverse function, okay, and then?
And then take the pair of that I and the identity and go to g squared.
The second step you want to do is like the first step you should do. I mean, we have a way, remember the pairing function that gets me here as soon as I give it two arrows, one from g to g, and in this case another one from g to g again. So in this case, you would like to take a g, let's say, take an x, you would like to do this. They cannot duplicate it, it's not delta. You want to create a copy of it together with the unit element.
But the unit inverse, right?
Yes, of course. Thank you. So this is like that, let's say. Okay, so what do you have that does that? So it's not delta. Delta would just copy it. You want to call something that leaves it intact, which is the identity, and something that inverses it, which is the I. So here you pick the identity sorry, what was it? The inverse. So if you start from an x, you are now mapped to, it's the other way around, the way I wrote it. Okay, so it's like this. You reach this. And now what can you do with it? You have a pair of elements of G. You can multiply them, right? And now what do you reach? You reach G. So now we have one way, like I was thinking before, we know where we start from a G, you duplicate it and you pick, and you leave it intact at the same time. Sorry, you duplicate it and you invert it, and then you multiply these two. And this should be the same as, it's not the identity now.
Oh yeah, it's something like you.
Yeah, so this is what I was thinking that I had raised before, and I was asking myself, how do I fix this problem? A different person just picks the identity, but there is still something to fix here. What's the problem here? Do we see it? Lazarus? First, what's wrong with it? And then how we fix it? I have a type error, right? The source of u was supposed to be 1, okay, a terminal object. And here I'm treating it as if it was as if it was a G. Do you have an idea of how we can fix this? Yes?
We could think of a function that destroys anything in G and produces the element of 1 and composes.
Okay, perfect. Okay, so the word was fine, destroys. You mean like it collapses everything to I don't know if it's more politically correct to collapse it or to destroy. Destroy it kind of gives me the impression that it deletes it, right? It's not that it maps everything there, but how do you describe this? I mean, that's the idea. I would like to have an idea of send everyone to the same element, but if I say something, it's lambda xu, I'm cheating again because I'm picking points. I mean, this is the function, if this was sets, this is the function you want, the function that takes every element and maps it to E, sorry. I'm confusing E and U, right? Okay. I should have used the same symbol. I mean, another name for this. But it's kind of cheating because, like, you need points again. You're saying it's a function that doesn't, maybe these arrows are not functions, maybe these objects do not have elements. So what is something that guarantees that I can somehow do this here? Yes?
One is a terminal object.
One is a terminal. Are you asking me or?
No, that's the answer I'm giving.
Okay, help me do that because I need the terminal object, but
It's a terminal object, so there exists a unique arrow, if I'm not mistaken, from
The-
anything to that. So we go from G to 1, and then from 1
okay, yeah, very good.
to G to
Because the way you said it, it looked like a hint, and I wanted the solution. Yes, okay, it's exactly this. So the idea is you break this arrow in two, and you say, okay, there is a unique arrow here, so I don't need to specify anything, and now this is you, right? And if you think about it, I don't remember if we have talked about it, but like, if you have what is called a zero object or biterminal, which means that it's terminal and initial, one of the things it guarantees is that from any object there is a path to any other object. Just go through the terminal one and you get an arrow. It's not the case here, okay? Even though I do have this, right? Even though in the category of groups this is true, here I'm in a category that I know nothing about. Apparently, I know that it has a terminal object, but maybe it's not a zero object. Maybe it doesn't have maybe it has a different initial object, or maybe it doesn't even have an initial object. But this one I can do because this is guaranteed by the terminalness of one, and this is on my givens. I have a U from 1 to G. Okay? Yes?
If we look at it element-wise, how are we guaranteed that it's the same initial small g that ends up through the operation collapsion and then...
Okay, if you look at the points, so you are back in set, right? So you say these are functions and these are sets and stuff like that. This thing, what set is this? It's your favorite singleton, right? So if you were in sets, this would be like your favorite singleton.
At this point, all information is lost from about where we started from.
Yes, but remember Lazarus' answer, he didn't even need to look at the input. He doesn't care what input he got, because he gives always the same output. The output is the identity. So essentially, this comes from a set G to a set G, and what it does is, I pick an input, I don't even need to give it a name, I don't care what the input is. What will I output? I will output the identity of this group. So I'm not losing any information that I was interested in. Essentially, what I want is to go from a group, from a set in this case, because I'm in the category of sets, and map everything to a specific thing that I know exists inside here. And I know it exists because of this. Make sense? Okay. Okay, it's time for a quick break. Let's make it really quick, like 7 minutes, please. So 12 and 10. Yes, okay. 12 and 10.
Don't forget to undo the changes you made.
Yes, thank you. I will undo them right now. It's like that. Okay, so we have managed to describe this as one of the laws we want, but actually we are not done, not even with inverses, because this just describes that it's a right inverse, right? So I would have to do the same for a similar thing for the left inverse. Okay, now I'm done, and I have to do the same thing for multiplication to say that it's associative. And okay, like maybe let's try to do one more, or come back to it if we have time in the end. And this can always be like an exercise. But let's say I've defined now what a group object means. Obvious questions. Every time I learn a new categorical concept, I need to test it on categories I know. So the obvious question would be, what is a group object in the category set? And I mean, probably you can guess it. A group object in set is, yes? A group, okay? So a group is just a group object in this category, okay? Surprisingly, it makes sense also to ask what is a group object in the category of groups. In a sense, what are the groups of groups? Like in the world of groups, what are the world of groups? And this is a very nice exercise, and within it you will need as a lemma, I think it was the last homework of the previous set of homeworks. Can anybody guess what, I mean, if you haven't seen it, it's difficult to guess it, like immediately, as soon as you find out what a group object is. I mean, it will end up, if it exists, it will end up, the group objects in this category will end up being certain groups, because after all, I'm in the category of groups, so all I see is groups. So, will it be all of them? It's a possibility. It will not be all of them, it will be a special kind of group. It will end up being the abelian groups, the commutative groups. And the same is valid for monoids as well. So like, okay, but when I say a monoid, that means I have to define first what it means to be a monoid object. But I mean, you guessed it, just forget about this thing, right? And you have the laws of a monoid, so there's a concept of a monoid object in a category. The only reason I started with groups is because in this audience, groups are more familiar, so I'm starting to define a group object, and I'm telling you, you can also talk about a monoid object and stuff like that. So yes, the group objects of the category of groups end up being the abelian groups. I mean, prove this. There's a very nice little lemma you need, and the lemma is the last, I think, the last exercise of the previous set of exercises. Just one last thing. In the category of topological spaces, if you know it, you will guess it by the name. If you don't know it, you will not care about it. Yes?
I know it exists, I don't know exactly what it is. Is it a topological group?
Yes. Okay. So a group object in the category of topological spaces ends up being something interesting that is studied in topology, which is called a topological group. Essentially, it's the two things that coexist there, the notion of an open set and continuous things, and the operation play well together. Essentially, you can say that the operation is continuous or something like that. Or you can say, this is just a group object in the category of topological spaces. Okay, so now the question is, like, as soon as you define something like that, what would be a way to go from a group object in a category to a group object in a category? And if you remember that the group object is not just this guy, but it's the whole configuration that looks like a T here. I mean, the first time you see these definitions, they seem extremely abstract or weird. And as soon as you see a couple, it starts to be a bit obvious. I don't know if we have reached this point yet, but if not, I don't think we're very far. So these things have a chance of being group objects. And they are group objects if and only if they satisfy all the laws, of which I only wrote one, okay? But all the rest can be written like commutative diagrams as well. So what would be something that gets me from a group object to a group object? I mean the same category, right? I want some group object in the category of set to a different group object in the category of set, for example, or some other category. So the idea will be like, okay, let's focus on this guy, even though I know it's not just this, it's equipped with all this extra structure, but probably something that would get me from this group object to a different, from the green group object to the red, or I don't know, to the whatever, yes, to the purple group object. First of all, this probably is not called G. Let's call it, I don't know, H. Notice that 1 here does not change, because 1 is the terminal object of my category. If I don't have 1 over there, I don't have a candidate for a group object. I don't have a group object, okay? So it's like that, and I have like the... it comes with its own operations. I don't like this convention. I went from G to, I know I'm kind of psycho with those things. Okay, so since I went from G to H, I will go here to V, to N, and to J. Okay. Okay, so what would be an arrow that gets me from the green group object to the purple group object? Can you guess where should I start from? Maybe you can guess what it will end up being. Okay, it will not be such a spoiler, such a surprise anymore, because we have seen a lot of stuff like that. So maybe you kind of have a feeling of where this is going. But Areti? So the idea of, yeah, so this was like, this is an answer similar to what Panos had given earlier. Like we want to map the arrows as well. And when we try to do that, it was not exactly mapping the arrows, although this can also become precise in a sense, but we have not seen this yet. So let's start, it will end up being something like that. We have to worry about the arrows, let's say. At least we have to worry about the arrows. And what does it mean, worry about the arrows? So first of all, let's start with the thing that's pretty straightforward. It should get me from the G to the H, something, first of all. So I need an arrow like that. Okay? Now, as soon as I have an arrow like that, whether I want it or not, I also get, together with it, an arrow like, I'm trying to make it dashed here, I think it will work, an arrow like that. I don't know if dashed helps, which is the same arrow, because this is G and this is G. And also an arrow from here to here. Which arrow would that be? No, I don't like this, sorry. I will make this just thinner. So let's call this phi. This is phi as well. And what is this arrow here? The one that goes from G cross G to H cross H, are they? Phi. Okay. Yes, so it's phi cross phi as well. It's phi cross phi, right? And here, I mean, I don't even need an arrow. Here it's an equality, right? Okay, so I have all those arrows. What does it mean that I need to take care of the extra, need to care of these arrows, the structure, the group structure I have there? It means that all things have to commute, because look what happens here. Let's try to draw something that could commute. So if I start from here, I can go here and then here, right? Alternatively, I could go here and then there. So I don't know if you see it, this is a square. It's a rectangle, right? I mean, it's one side, the next side, the other side, the next side. Okay? Is it a square for everyone? Okay. And this has to commute. And everything that's there has to commute. So if I translate this, like, what will I get? If I say, let's say I'm back in set to see what this means there. If I get let's translate this. I want to do phi cross f and then multiply in the other thing, so it's like the n of this should be the phi of m. Am I right? I'm trying to describe the phi of m, which is this, should be the same as the n of this, which is this. Okay, so if I give it the arguments it needs, it means that I have like multiply, what is the type of argument I need to give here? It's phi cross phi, so I need to give it a pair of things. Let's call them A, B. Where do A, B live? What's the type of A and B? Yes? Then in G, right? Okay. And this should be equal to, I will check this, to this. I'm just giving a point, because now I enter a set and I know what equation of functions means and all that stuff, and I know I have points and blah, blah, blah. So in the left-hand side will end up being phi of A multiplied in H with phi of B. And on the right-hand side, I will have A multiplied, no, sorry,
Phi A times B.
yes, thank you. Phi A times in G, B. So if I look at it, I realize now that this commutativity is just what? Or the other way around. Yes? That phi is an homomorphism, but remember, being an homomorphism in the lambda of groups means you have three things. So which aspect of the, like four things actually. First of all, you have a carrier function, and homomorphism knows its underlying function, and three more things. It respects the operation, the binary operation, it respects all operations, the unary operation, the inverses, and it respects the identity. So it maps the identity to the identity. So this thing that we just described, this commutativity corresponds to the fact that phi respects the binary operation. If you see the other commutativity, so this commutativity, this is easier to imagine in this way, you don't need a lot of 3D here. So this commutativity corresponds to the fact that phi respects the inverses, and this commutativity, from 1 you go to H, or directly from 1 you go to, like you stay to 1 and then you go to H, corresponds to the respecting the identity element. So if you translate all this, it means we have defined group objects, and we have defined what it means for arrows among group objects, so we can, in any category, I have a new category, which are all the group objects of C and arrows between them, right? So if you ask, so the question that we answered already, but we haven't proven it, is that groups, this category here, is just, or isomorphic if you like, or equivalent, I don't know, to, sorry, set here, is equivalent to the axial groups, while if you replace group here, you get the abelian groups. Check this Zulip for help. But even if you try to prove it, essentially, you will end up rediscovering this important lemma that is already an exercise. But I didn't give it a name. I didn't want to think that it's important when I gave it. Okay, yes?
If you take the group of abelian groups,
everything stays abelian. I mean, yes. So
is it all the
it's like you have already reached the total groupness of things in the level of abelian, and every object there satisfies what it needs to satisfy to be a group object inside the commutative groups. And it's the same with commutative monoids. So if from monoids you get the commutative monoids, if you enter the category of commutative monoids and you ask what are the monoid objects here, it's the commutative monoids. Again, if you like to try to prove this, I already said what is the main lemma you will need, but this can end up being a major hint. I think if you try to prove this, you will get stuck somewhere and you will figure out what you need to prove, and this is actually the lemma that was an exercise. Yes, Sarati?
Ουσιαστικά το group object, και αν βάλουμε κάτι
Yes, it's a very bad name in the sense, because I'm saying that G is a group object. I'm lying, it's not G. It's this thing that is a group entity. I don't know, I should avoid the word object because these are objects. This is an object, an object, an object, an object. And I'm saying that this object is I mean, even in the category of set, think of a single set that you like, it can become a group maybe in more than one way. Like you define a different maybe. So in this sense, you would have two different group objects with the same, even though they have the same central, let's say, object there. And it's similar with product. We say that this object is a product of A and B if and only if blah blah. No, it's not just the object. But we understand it. Okay, it's kind of bad, but you get used to it. Okay, so the major thing that I want to do today, which is like I didn't want for us to stop having classes without doing this. If I guarantee this, I'm okay. There are like two more things. One is the natural numbers object. Okay, so let's go there. Because we have seen the type of natural numbers, not completely. We more or less know what we should expect. We have seen it in a programming language setting. In the first or second class, we define the data natural numbers. They have two constructors and stuff like that. But we haven't seen it within the framework of the type theory. We have developing it. We have been developing. So, kind of simultaneously, I want to see it as in a general setting of categories, and then see it in type, how this manifests in type theory. So I want to define the same thing. I want to look at what's the role of the natural numbers, let's say, in the category of sets. There is a specific set that satisfies such and such things. And if you're doing like axiomatic set theory, there is almost an axiom, it's very unnatural, that it tells you there is a certain infinite set that satisfies such and such stuff. Maybe it would be more natural to say in the category of sets there is a natural number object, depending on how you look at it, but the idea is how would you describe it? So essentially a natural number object will end up being some object, let's call it n, for mysterious reasons, and again it will not come by itself. And the idea is that if I ask what are the natural number objects in the category of set, I will get back natural numbers and all isomorphic copies of natural numbers, of whatever way you have encoded the actual natural numbers, and the successor, and the zero, and pretty much that's it. Okay. So ideas of what else I need. I mean, if you remember a bit, what is the structure that what is a piano structure? We will figure out the initial little diagram that I will have there. Yes. From 1 to this thing, let's not call it 0, let's call it O. But yes, okay? What else do I need? So what will be the role of this thing? If I look in the category of sets, this should be the element, since it's from 1 to something, it's just an element, the 0 element of the set of natural numbers. Okay, am I done? And the successor. So it doesn't look like a T, like the previous thing. I will draw it like that. It's more usual to see it like that. Okay, so as soon as I have this, I have a candidate for a natural numbers object. But I need to kind of see what is essential about it in the same sense that I saw the group laws there. So what should I do there? And the idea is now that I will pick of this thing to be the best among all natural numbers objects. So let's try another candidate for a natural number object. Again, one will be fixed, and instead of copying it and saying this is equal, I will just leave it the same way here, and I will say, okay, let's say that Konstantinos here has his favorite candidate for a natural numbers object, which means what? It's now what was the color I used here? Green. So now the green things are not, they don't look like these, they look like that. And the idea is that somebody else comes, okay, let's complete what is missing here. So you have your own notion of 0, which I will call, I don't know. I will call this H, and I will call this E. Okay. Not good names, but it's okay. I forgot to paint green this thing. Okay. So what would be an arrow from the green thing to the purple thing, and what should I demand of this thing to go to? So if you remember, what's so important about the natural numbers is that we're allowed to define functions leaving the natural numbers by doing recursion. And in order to define a function leaving the natural numbers, going out of the natural numbers, I need to provide two things. I need to say what is the zero element, right? So I will do something like, okay, I will pick an element from, in this case, A. This will correspond to the zero. And the other thing is I need to have like a end of, as soon as I have an end of function in H, I can iterate this many times in order to get to 42. And this will essentially define a function from the natural numbers to A. But even if I forget all this intuition, which I probably have because I have defined the recursive functions in my life sometimes, or because I have proven things by inductions, we'll talk about this, and I ask what should be arrows from the green to the purple, is there an obvious answer? Like, remember what were arrows from green to the purple? There is a major arrow from something, and then I see all the other things that should get mapped and things that should commute and stuff like that. So obviously I will need I will not say function, an arrow from N to A. The idea is that as long as you have this, there is a unique, maybe I should emphasize this like that, there is a unique function here. It's the same one, okay, because it's from N to A, such that these things commute. So this gives me the natural numbers as some kind of initial thing. It's the best among all those things, this initial thing. And so this means that anytime I want to define a function leaving the natural numbers, all I have to do is, like if I want to define a function from N to A, all I have to do is give these two things and then ask for the recursion pretty much to do this. And I get to pick a name for this, and I could call it something like, I don't know, the rec from recursion. What are its inputs? Well, I only needed E and H here, so I will codify this like that. Or I could give it some other name, like when it was the product, that I again, in the product I was gaining functions going inside by functions going to, by these inputs. I had one going inside A, one going inside B. If I had called them F and G, I could call this and I could say, okay, this is the pairing of F and G. The point is that as soon as you have a diagram that guarantees existence and uniqueness of something, you can see this as a way, anytime then I would like to define something from A to N, I can reduce this to all these things that the diagram needed. In this case, I can reduce this to picking an E from 1 to A, and picking an H from A to A. Sorry, this is from N to A. This is wrong, okay, from N to A. So if you want to define, one way to do this is reduce this to, it's enough to do this, then ask for the diagram, give me the uniquely determined arrow from N to A, this will be my function. And this is exactly what we are doing here. We're saying I want to define a function that gets inside A cross B. How do we do that? Let's remember this. You have some, I don't know, domain D, and you go to A cross B. How do you define this? You say f of D is equal to, and then you say, there are two things I need to give. But if you see these two parts, essentially what have you done? You have mapped D to that, so you have given me a function from D to A, And you have also mapped D to that. So you have given me a function from D to B. And the idea is you put this together, and this is how you define functions going inside products. And the dual is, happens when you define functions leaving sums. If you want to go from A plus B to some arbitrary codomain C, I don't care, how do you define functions like that? You say by pattern matching, right? You say something like, if it's a left of a little a, I will map it here, while if it's a right of a little b, I will map it here. What have you done essentially? You have mapped the arbitrary element of a to some expression of type C, so you have given me a map from A to C, and here you have mapped the arbitrary b of type B to some expression of type C, so you have given me also a function from B to C, right? So this, you would call it pairing of FG, and the other thing you would call it co-pairing. We have also have some like fancy notations like FG for the pairing, and I think we have ended up using this for the co-pairing, and so on and so forth. Okay, so as soon as you have a diagram that has this, there exists if you have these things, as soon as you have dotted lines with a bang here, you gain a way to define functions. That's my point, okay? Questions? So the obvious, okay, an obvious question is, so in the category of sets, what would be the natural numbers object? It ends up being the natural number, all isomorphic copies of the natural numbers. What about the category of types that is of interest to us, and what this thing will end up being? Before we go there, I would like to show a different way to organize this same concept of this same diagram. As soon, okay, yes.
Don't we kind of need to ensure that S is like on-to-one, basically, or something like that? The successor is a successor, basically.
Good question. This is one of the Peano axioms. I don't think this is part of the natural numbers object definition, the way I'm saying it. And now the question is, why would you not collapse this? So yeah, maybe. If I try to...
Specified by, like, if you make the purple thing, the green thing, maybe the uniqueness somehow helps.
Say it again?
Maybe if you take the fact that if the purple thing is the same as the green thing, you have the uniqueness over there, maybe that somehow guarantees it.
What you do have, okay, this is something to check. Should it satisfy? Should extra things be satisfied about this S here? But what is indeed the case is, since I'm defining the natural numbers object to be an initial thing, I'm defining by universal property essentially. It means that I gain uniqueness up to unique, the strong uniqueness up to unique isomorphisms for free, which means that if you have a different natural number objects, you play the same game that we played with. I mean, you shouldn't, because we have already know that initial objects are unique. So you have two options here. Either you actually go through the trouble to see that you have a category of natural number objects inside your category, and this is initial, so it's unique and you're done. Or you say, okay, let's say that I have some other copy and that is also a natural numbers object that has all this property, this diagram, and guarantees the existence, and then you want to prove that this is actually an iso, because you want to prove that this is isomorphic to n prime, and pretty much you will use once the fact that this is a natural numbers object, and once the fact that this is a natural numbers object, so this composition will be the unique that makes things compute. But you also have a different arrow from n to n that makes everything, sorry, I said compute, I meant commute, which is the identity, so it means that this composition after this will be the identity. It's exactly the same thing we did proving the uniqueness of products or coproducts. It's exactly the same thing. So we do have uniqueness of n and o without these things, so probably inside the category of sets, maybe this becomes a theorem. But I don't want to say this like with 100 homework. So yes, you should figure it. It's better if you figure it out yourself. So let's figure this out in Zulip. So the thing I wanted to show here, because extremely general, but it's an opportunity I have to do it here in the language of natural number objects. I want to encode this whole thing if I'm somewhere that I have sums. And essentially what you have given me here is two arrows entering this object N. One called O and another one called S. So if you give me two things what did I want to say? That go inside N. So you have like, if you have this, then it means these two determine there is an isomorphism between these arrows here and pairs of arrows here. So I could replace these two arrows that you have with a single arrow here. Because as soon as I have an arrow like that, I can ask for its components, let's say, and I will get here that I can name them like O and S. And the idea is that I could have defined, this is equivalent, a natural numbers object instead of these green things. It could be these green things, okay? And I would say that an N and O is an initial in this category. So if you come with a different one, like EH, there is a unique way that I can map mine to yours. I will leave this diagram here. This we will not have time, or actually it's not really a part of the things we are saying here. This is a way that you can bunch any algebraic structure that you can think of as a bunch of things of this type. A sum of things getting inside your carrier set. So like a group would be something like this. And the idea is that, okay, I don't know if I should mention this now, but you can define pretty much what a group is by looking at this thing. Okay, I will say something just for you to hear the terminology, and maybe if you're interested, we expand on Zulip or you look further to it. Consider this pretty much is a functor here. So that, let's say I have this functor here. It will look like a polynomial, and that's the idea. So if I look at this functor, I can define what an F algebra of this will be to be an initial object that goes from things of like that to things of like that. I want it to be the initial thing. And these things will correspond to actual models of my theory. If I'm doing group theory, this will correspond to groups. If I'm doing, ring theory, this will correspond to rings. So, but for groups, I will need to change my functor. It will be something like f of x equals 1 plus x squared, or x times x. But, okay, maybe I should, yeah. I don't know if I regretted mentioning this. If you are interested in giving like semantics to algebraic theories, or even some certain kind of products, you will come across the idea of F algebras or F coalgebras, and this is like the beginning of where things start. We can expand this on Zulip if you like in the next days, or you can look it up. I will not need this here, I just wanted to mention this generality. But the fact that this shape can be given as that, I think this is like neat, and then I have a simple commutative square to worry about instead of this like maybe kind of weird thing. Now, yeah.
The fact that you can go from 1 plus n to n, like in that specific way, to kind of give me the vibe of the fact that like 1 plus omega is equal to omega. Is this in any way related to that?
I always say that if the question is this in any way related to that, always the answer is yes. I mean, a relation is, at some point in time, somebody phrased this question and they are related. I don't think so in this sense, but we may figure out a way that this will be related to that. But I want to say no, because if I swap these things, nothing will change for my presentation, because the plus is commutative, co-products are commutative in the sense, while if you think of omega plus 1 and 1 plus omega, the plus is not commutative there. So I want to say no, but I will not say it very, very strongly, if that makes sense. Okay, so I mentioned the natural numbers object because I want to see what happens with the nut type, which I haven't discussed. And the formation rule of the nut type in type theory is extremely simple. I want to form this type. I say, what do I need? Nothing. This thing is already a type. Okay, it's not a type constructor, it's already a type. So the kind of more interesting thing is how I introduce elements of this type. And okay, what is the way to introduce elements of natural numbers? Somebody? Yes?
0 is a natural number.
From nothing, you can already say that 0 is a natural number. Which 0? The natural number 0, okay, because maybe you are doing integers as well, but I will not decorate it with a subscript. And what is the other way?
If n is a natural number,
Yeah, if n is a natural number, then the successor, however you want to write this, is a natural number. This is the introduction of O, and this will be like the introduction correspond to S. And the crucial question is like, how do you eliminate natural numbers? How do you use a natural number? And this is where this idea will come now, that it should be something that allows you to define functions by doing recursion. So let's gather all the data and see what are the complications that we have when you are doing type theory. Because the recursion we have seen here, this is the major complication I want to address. The recursion we have seen here goes from n to a, it's just a function leaving n and landing in a set. But when I am in a dependent type theory, the complication is that I have dependent functions. So it's not enough for me to have a way to define functions from n to some a. I should be able to define function from n to a dependent a that depends on its input, right? So let's try to put all the data we have on this and see what we need to add or to hide. I think we can pull this off. Okay, so I don't have this on these notes, but we can do it. Okay, let's try. Okay, first of all, what am I trying to do? I'm trying to define something by recursion. Equally now you should think I'm trying to prove something by induction. In order to prove something by induction, we need to remember how we have visualized properties, let's say, of natural numbers. When I write P of n, these are corresponding to type families over the natural numbers. So essentially what I have is something like that. I have a type family. I can write it like this. Or I can write it like this. These are synonyms. As soon as you have n, then A of n is a type. Pick your favorite. I don't care. The idea is that, remember, you have the natural numbers here, and over them you have these things hovering, these balloons. So this is like 0, 1, 2. So this is the type A of 0, the type A of 1. So if I see propositions as types, the idea that n has a property corresponds to, like let's say that 2 has a property, this is represented by this type, and here are all possible proofs that 2 has this property. Maybe I want to prove that for every natural number there exists a greater number than that. I don't know. I want to prove something, and the idea is that I want to express this as a dependent family, and the idea is then that instead of seeing this as a proposition, I see this as a type, Which type? The type of all possible proofs that its argument has this property. So now is the time that recursion will become induction and vice versa. Because if you think of what you're used to doing in induction, you do what? For the natural numbers, but it's the same principle for any inductive type. You say, okay, I will do two things. First of all, I will prove the base, which means that I will give a proof of P of 0. Goes here. And then you say I will do the inductive step, which is to show that for each k, if P of k, then P of the successor of k. I'm not doing anything new at the moment. Okay, but so here you need a proof of that. But what does it mean to give a proof of 0? It means that you say, okay, give me, I want to define essentially, when I want to define that for any natural number n, something happens, P of n, essentially what I need to provide is a function that given any natural number gives back a proof that this natural number has this property. So how will I define a function from the natural numbers to all this space here? By recursion. The complication is that usual recursion that I have learned so far doesn't allow the codomain to vary according to what the input you gave me, because I don't want to keep proving the same thing. This vary, right? This is the collection of all proofs that 0 is nice. This is the collection of all proofs that 1 is nice, that 2 is nice, and so on and so forth. So it has this extra complication that we'll take care of now. But I do have dependent functions, so I would like a recursion that can work with dependent functions. A recursion that I need to say for 0, I need to map it to some element of type P of 0. Right? So give me 0, give me a natural number. If it's 0, I will give back a proof of 0. This is exactly what I'm doing here. While here, if you give me a k, I want to prove something that maps proofs of the fact that k was nice to proofs of the fact that the successor of k is nice. So this is exactly the recursive call that I will have, because when you're defining a function by recursion, here you're allowed to access f of n, which would be like exactly this thing. It's an argument. This is essentially the inductive hypothesis, okay? So let's put this thing and see what we need to have in order to say, if you have all those things, you have the right to say that you defined an inductive, a recursive function, even dependent function. Okay, so let's see. First of all, what do I need to provide? A type family, right? So I need to have this. I don't know if you prefer to see it. There are many things, so instead, this line will be very long. So instead of being long, I will write one thing below the other. So first of all, I need a type family, and I can write this. Let's write it like that, because I have already written it. So I have a type family A. I'm mixing A's with P's here. Okay, I'll leave it as A. Okay, what else do I need? I need to pick a specific element for A, which will be like my basis, right? Or the 0 step, or whatever you want to call it. And I will call it B. And this is where does this belong? This is the point. This is the easy point, yes? A of 0, exactly. I cannot say A, it would be a type error. It's something of A0. What is the other thing I have to do? I have to be able, at any step that I am, have a way of, if you give me some proof here, providing you with a proof of the next step. Okay, so how would I do that? Let's write that down. So let's call K, I'm following this notation here. So K is the index of the point that I have verified so far. So like K is a natural number. What else do I need in order to provide a proof for the next? Somebody? Yes? Something of type A of K. Okay, so how should we call it? I don't have a good name for it. Let's call it y. I don't know. A of k. And if I have these things, if from this, okay, first of all, I need a family of types. This represents the thing I want to prove. Secondly, I need a specific to singularly pick out a proof or an inhabitant of this type, and then given any k of this thing, and any k down here, this is my k, and any inhabitant over here, I need to be able to give an inhabitant of the next type. So what should I need to have an inhabitant of A of successor of I'm being confused here. Of K, thank you. And let's call it S to remind us that this is the inductive step. Okay. So if I have all those things, I should be able to get like a dependent function from essentially n to a, but instead of going from here to a dependently, I would like to carify, or am I doing carification or descarification now? I want to pull this thing over here. So I also want to say to have okay, let's call it E of type n. This is like that. And if I have all those things, I should be able to produce an element of A of E. Okay, so we have like, we don't have, but let's pretend we have like a couple of minutes still. All there is to do now is like figure a name for this and put all the components are needed in order to guarantee an inhabitant of AE for an arbitrary E. So let's do that. Let's call this int to remind us of induction. Let's put all those things together. So first of all, I need the A, which has this type. I need the basis, I need the step, and I need a certain E. And if I provide all those things, I get a proof that E has this property. I get a proof of, I get an inhabitant of A of E. Yes?
Shouldn't S be like S of k and y, or S should just be a function, like a current function or something?
S is a function, okay, I get what you mean. S is a function because you see where S appears, it appears only in this context. So this thing, S is dependent on these things, and this type is also dependent on these things. So S is not just whatever symbol you think.
Shouldn't that be like a notation or something, or is it okay like that? For some reason.
Okay, maybe. Okay, so you're saying that maybe I should have this here? No.
I mean, either S should be a function from the naturals to A of k, k natural to A of k, to whatever you have on the right, or it should be S of k and y, maybe. I don't like the fact that k and y don't appear in S, basically.
You don't like the fact that, I mean, if I wrote it like that, you would be fine?
Yeah.
It's kind of anything that I write on the right hand side of this. I may emphasize. Sometimes I do it, sometimes I don't. Like I could write this like that as well. I was here. Yes, it's kind of. I mean, if I write it like that, I'm emphasizing this dependence. If I don't, it's implicit by the fact that this thing is only valid under this context. Okay, so these things will appear here, and I think I'm done with this. I think I'm not. Sorry, I'm not done with this, but I think this is okay. But we can verify this. What is left to do, which is kind of always the case, we have to give information, introduction, and elimination. Where are the vitas and the itas? And I have just realized that we haven't mentioned the free thing. Maybe I'll push this free discussion on Zulip. Because there's only one thing missing. So like, what should be the equations I have here? So I will write the first. So if you ask me to do this induction on a predicate A, on a type A, and you give me B, S, and your E is 0, what should this give back to me? So essentially I'm asking for a proof of A of E. Where this should be which proof? Yes, Konstantinos? No? No. Manolis? B, yes. This should be the basis. And the other equation that I have is like, if you give me this, let's try to figure this out and stop here, S, and now you give me the successor of something. What should this be? Let's figure it. How do you do this? You make a recursive call, right? You have to ask. Eventually, somewhere, we will need to use this thing. Use the same recursion, but with this thing. And now, where do I plug this? To S? Am I? Who agrees with me? Is it like that? Or the successor? No, wait. Not the to the S. Yes. S of K and that. You really want to see this as an argument. Wait, S is an inhabitant of which type? Of A of successor of K. So this is an inhabitant of
yeah, the thing on the left is also an inhabitant of A of successor of K.
no, yes, yeah, you're right. Okay, so this, so I need a K here, right? Yeah, great, okay. So, yeah, there you go with the vitas. Try to figure out the eta. So pretty much the complication here was this, and I think we managed to do that, which means that now we have officially a way to do induction. Every time you write induction in lean, induction, I don't know, on some variable with that, the goals it reduces you to are pretty much these. Some of these you already have, so you will not see them as new things, but it's like provide these things, and this will let you prove. Okay, because if you move this here, this will become P, E, N, A of E, and this is what corresponds to for all E, N, A of E. Yeah, okay. So, okay, didn't have time to go through the free thing. I'll try to do this either on Zulip, because I'm not sure if I'll be able to give a lecture on Friday. Either, it's a small discussion. We could do this on Zulip. Sorry, Sotiris, maybe you stayed all this time for this. Yeah, okay, so I think this is it.